This is the first of 3 videos about the domain name system, or DNS. So let's look at a URL for a second. If we look at a basic URL like you would put into your web browser, it has 3 basic parts. It has first, at the front, the application protocol and port. So this is saying that we're going to be requesting a file over HTTP, and by default that means port 80, a TCP port 80. You could also tell this URL after the host to be some other thing, say port 1001 or something, but by default this means port 80. The middle part of the name is specifying a host. So in this case, cs144.scs.stanford.edu. This is a human readable name delimited by periods into 4 parts, and it's specifying the actual node that we want to contact. The last is then the file. So this is the application level for HTTP, the application level specification of what file we want to request, HTTP. And so the question is, so far we've been talking about the internet in terms of IP addresses, usually IPv4 addresses. But when we type a URL, we have this human readable name describing the computer or the host that we want to contact. And the question is, how do we translate this human readable name to an IP address? Well, it turns out you can, of course, enter a URL without using a host name, instead just by entering the IP address. So you could, rather than typing cs144.scs.stanford.edu, you could actually write the IP address that's associated with that name if you'd like. But these human readable names are very, very useful. And people realized that human readable names are useful just from the beginnings of the internet. And so way back when the internet was tiny, there was this file called host.txt. And it turns out that every single host on the internet was in this file, host.txt. And it was maintained by the Network Information Center. So it's maintained at SRI, so the srinic.arpa, at this particular IP address. So if you go and read RFC 952, it talks a bit about this. And essentially, if you are a node on the internet, what you would do is periodically contact this node at SRI and use a file transfer protocol to download a new version of it. And this new version would have all the new hosts, and then you'd be able to map those host names to IP addresses. Of course, if you don't have too many hosts, this isn't bad, but generally speaking, the network capacity required by this scales to the n squared, in that periodically n nodes are going to request a file that's order n in length. So this was not seen as a scalable, good long-term solution. It was fine with just a couple of hosts, but as the internet grew, it quickly became a problem. And this is what led to the birth of what's called the domain name system, or DNS. The basic problem that DNS is trying to solve, the basic task it's trying to complete, is to map names, human readable names, to addresses, or more generally these days to values. Originally it was to map to IP addresses. It turns out nowadays you can use it for much more. And there are a couple of design considerations for the domain name system. The first is we'd like to be able to handle a huge number of records, right? In theory, there are 2 to the 32 IP addresses. We should be able to map names in that kind of order. Furthermore, we'd like to have distributed control. One of the problems with host.txt is there's this single centralized repository. It should be that we can say, this set of names, you can manage them. This other set of names, you can manage them. So Stanford, you can manage names under Stanford, but Amazon, you can manage names under Amazon. Furthermore, we'd like this system to be robust to individual node failures. It shouldn't be that if one node goes down, the entire domain name system comes down. Because if that's the case, then suddenly we can no longer map names to addresses, and lots of things would grind to a halt. So we want to be robust. And so this might seem like an amazingly challenging problem. We want to handle billions of records distributed hierarchically across the entire internet, which is robust to failures. But there are 2 things which turn out to make this problem tractable, and make the design feasible. The first is that this database that maps names to values is read-only or read-mostly, and that there are updates to it, but you generally expect that it is going to be read much more than it's written. It's not like there are nodes coming in and out all the time, but nothing compared to the rate at which we're looking nodes up. Furthermore, we don't need perfect consistency. You can have something called loose consistency. So if a node connects to the internet, or if, say, a mapping between a name and an address changes, it's okay if there's some delay before everyone sees that. It might be some people see it a little earlier than others, but it's okay if there's some delay. And so it turns out that these two properties together, that it's a read-mostly database and that it's okay if things are slightly out of date, allows DNS to have extensive caching. The idea is that once you have a result, you can hold on to it for a long time, and then maybe when it expires, request the new result. But rather than have one place, say, that has to be asked for everything, you can ask someplace once and then cache that result and answer it for other people. So you can look up a name and then keep the result for a long time and then use it to answer other queries. So recall that one of the requirements is that names be hierarchically administered. That is, you can distribute the administration of names. And to accomplish that, DNS uses a hierarchy of names, and we're all familiar with this. So at the top, there's implicitly what's called dot, or what's called the root of the DNS namespace. It's nothing. It's a nothing, right? It's an empty name. So these are called the root servers, just dot. Then beneath them are what are called the top-level domains, TLDs, such as edu, com, org, US, France, China. Then underneath each of those top-level domains, there are what we often think of as domain names, say stanford.edu, or cisco.com, or baidu.cn. And of course, within those domains, the owner of those domains can hand out additional names, additional domains. So for example, at Stanford, generally there's just one level of names below Stanford. So there's cs.stanford.edu, www.stanford.edu. Berkeley has another layer. So there's cs.berkeley, there's the CS domain, and then there are names underneath the CS domain, like www.cs.berkeley.edu. Similarly, Google has maps.google.com. So now the way DNS servers work is that there are these hierarchical zones. There's the root zone, then the TLDs, then the domains, and then there can be subdomains. So Stanford, for example, as you may have seen so far, it does have a subdomain, SCS, managed by David Maziere. And the key thing is that each of these zones can be separately administered. So Stanford can grant David Maziere the domain SCS, so it'll answer questions about SCS, but then David can completely control all of the host names underneath SCS. Similarly, edu can grant Stanford the name Stanford, but then it's completely up to Stanford to manage all of the names beneath Stanford. Furthermore, each zone can be served from several replicated servers. And so rather than there's being one server that serves Stanford's name, there are in fact many servers replicated. And there's some rules as to how they're replicated. So the idea is that if one server goes down, there are others that can still answer questions about Stanford. So it turns out the root zone, so the zone you'd ask for, hey, who do I ask about edu? There are 13 servers labeled A to M, and they're highly replicated. And so there's sort of this bootstrapping process of your computer comes up for the first time and wants to ask a name and it knows nothing. Well, it needs to talk to a root server in order to contact, say, a top-level domain server. But how does it find out the root servers? It turns out these are generally just IPs that are stored in a name, in a file in the name server. So the name server comes up, and it has some IP addresses for root servers. And then the first query that comes in, let's say it's for stanford.edu, it knows that it needs to talk to the edu servers, and so it can ask the root servers, hey, who has edu? Then when it gets the response, who has edu, it can contact the edu servers, hey, who has Stanford? In addition to having these 13 different servers, they're highly replicated through something called Anycast, IP Anycast, where it turns out that there are many machines that have the same IP address, which basically causes you to contact the one that's closest to you. So this makes the root servers highly, highly robust. Often when you hear about large-scale distributed denial of service or DDoS attacks against the root servers, this is exactly what they're talking about. That people are trying to attack the DNS root servers to to basically cause the DNS system to grind to a halt. As of yet, nobody has yet succeeded. There's so many of these servers, they're so robust, and it turns out their job is so simple, people haven't been able to do it, but they keep on trying. So here's a map of the DNS root servers. So A, B, C, D, E, F, G, H, I, J, K, L, J, K, L, M. And so colored, so here are all these different A servers, or A server A, B, D, E, G, H, L. And then for the Anycast instances for C, F, I, J, K, M, you can see that they're spread all over the world. So this means that, say, if you're somebody in say Saudi Arabia, and you want to issue you're a DNS server and you want to issue a DNS query, you don't have to go very far. There's some that are very close by. Okay, so that's the basic naming architecture and sort of a sense as to what DNS servers and how they're structured, these hierarchies. So what does a query actually look like? So there are two kinds of DNS queries, recursive and non-recursive. A recursive query asks the server you contact to sort of resolve the entire query. So you're asking it a question, and if there's many steps to the question, then it should ask each of those steps. As opposed to a non-recursive query where you're going to contact a server, it's just going to answer one step of the query. And I'll show you why this difference occurs in a second. And you specify just a bit in the query to say whether it's a recursive or non-recursive query. So DNS usually uses UDP port 53, and there's a 512 byte message limit. You can use TCP port 53, and then all the DNS messages have a 16-bit length field, so you know how long they are, since they're not datagrams, they're a stream. So let's say that I'm a client. So here's me, and I want to ask a question of, hey, what is the IP address associated with www.stanford.edu? So using DHCP, I have an address for a DNS server, and so let's call this here resolver, and so it has some address R, and so I send a DNS request or DNS query saying I need the IP address for www.stanford.edu, and I send this message to the resolver. So I'm asking for address of www.stanford.edu. And I ask this as a recursive query. So the resolver is going to resolve this entire query recursively for me. Well, let's say my resolver has nothing cached. It doesn't know anything about the world. It just has the IP address of some root servers. Well, the first thing it's going to do is it needs to figure out whom to ask a question about edu. So where are the servers for edu? So it sends a query to one of the root servers saying, hey, whom do I ask about edu? This is a non-recursive query. I can't ask the root servers to answer the whole query for me and start contacting other people. They're just going to answer one step. They'll answer, hey, who should I talk to about edu? And the root will send a response saying, here's some information for who you should talk about edu. Now the resolver knows, okay, now I can cache the entry for edu. Great, I can put it in my cache. This is the IP address I should contact if I have a question about edu. Now let me contact that IP address. And it's going to ask edu, hey, who should I ask about Stanford? Again, this is a non-recursive query. The edu server is going to say, okay, here's some information about whom you should ask about Stanford. I can then cache that result and ask that server, so the domain server. So now I'm going to say, Stanford, what's the address for www? And Stanford can respond and say, aha, here's the address for www.stanford.edu. And then the resolver can cache this result. www.stanford.edu. Now the resolver can cache these values of, if I want to ask a question about edu, what DNS server should I talk to? If I want to ask a question about stanford.edu, what DNS server should I talk to? And what's the address for www.stanford.edu? And then it can return this result to the client. Here's the IP address for www.stanford.edu. And so that's the basic operation of a DNS query. It starts with the client asking a recursive query of the resolver. The resolver may then ask non-recursive queries to servers in the network in order to generate the response, which it then sends to the client. It could also be that the resolver had answered this question before, and so rather than go and ask all these servers, just answered from its cache. So if a couple minutes later another client asks the same question, hey, what's the address of www.stanford.edu? This resolver, rather than contact anyone can just return the cached result. And so if you ever hear the noise about here in the news, not the noise about DNS cache poisoning, there's this aspect of DNS which these attacks try to tackle, or try to take advantage of, which is that if you can get a bad record into the resolver, that somehow convince it that that www.stanford.edu actually points at www.evil.com or something, such that if you try to go to Stanford, instead you go to some evil hacker's server. If you can get that cache entry into the resolver and poison the cache, then anybody who asks that question is going to get that answer. And so later in the course, when we talk about security, we'll see some of the ways in which that can happen and some ways in which DNS can solve it.